find zeros. Well, what do we know can do it for us? The calculator, right? The calculator. So I'm going to use the calculator, but this is leading us, the reason for this problem is because the next section deals with Newton's method, which is an introduction into how a computer solves this. Okay? Just so we can understand the importance of it. Here it's just, we want to try and solve this problem. We get stuck at the end, so the technology will help us finish it off. So I'm going to come into I have a TI-89, but you could go to Wolfram Alpha and just put solve and type that in. I'm going to do solve 4x cubed minus 9x squared plus 6x minus 5 equals 0. I get through my calculator x equals 1.80255749.354. Now, you don't have to put all those decimals, but again, I'm trying to lead you into the next section, all right? That's what my calculator says. Anyone else get that? That knows how to use that, any of those features on their calculator? If you want to learn how to use your solve function, if you have a TI, it can do this. Now, what would we still need to do here? 1.802. What would we still need to do? Assuming we got that. Number line. 1.802, then we would have to do test points, plug those into the derivative. And what we would get is this. I'm going past that because of time, all right? We could verify it's a local minimum. Now on a test, I would never give you a problem where you'd have to use a calculator. It would turn out to be a nice thing that you can solve. But don't be surprised if you were to see a problem like this where it says find the minimum distance between a point and a curve. It's just that, what's that? No, that's the x-coordinate of the point. That's the x-coordinate of the point. So what we would still need is the y-coordinate. So plug it into the equation that we have for y. What was y? It was the square root of 4x minus 1, wasn't it? So if you go y equals square root, well, I won't even, just plug in 1.82. Oh, whoa. I used the solve feature on my calculator to get 1.082. I'd be happy to show you that when we take a break. So according to this, it looks like 1.082, 1.824 looks like the point. We got, for the x-coordinate, it was it 1.8? Oh, it was 1.802. Oops. 1.802. Let me double check that. I think I did the other calculation wrong then. Yeah, I did. 4 times 1.802 minus 1 square root of that. 2.49? 2. We're about to find out if this is right. How am I going to find out it's right? There's a couple of ways I can do it. Why don't I go out to this picture right here, and why don't I snap to the solution? And what's the solution? 1.8, 2.5. And the actual distance is 1.9. How do I get the distance? Go back to that capital D equation before you took the derivative and plug in your x and y into it. any computer science people here? I think I've asked that before, right? Are there any in here? No? Yes? Okay, so look. You know how it said snap to solution there? And it just popped to the answer? In my code here, this is the code that I wrote to make this thing happen. I should have somewhere in here but somewhere in my code I should be taking a derivative. Maybe I didn't. Okay. All right. I guess I went and computed the answer on paper somewhere else or had the computer do it, but all right, we're going to take a break. I think you all are ready for it, right? Let's say 10 minutes, right? Let's come back around 3. All right, I'd like to maybe do one more problem in this section, optimization. Because like kind of we had with the related rates, none of the problems are exactly the same. They all have different sorts of things involved. So I'd like to get something kind of different from what we've done already. Here's a classic, how about a very classic problem, one that a lot of Cal 1 classes will cover. Find the dimensions, dementia? Is that what you said? Find the dimensions of the cone with maximum volume, which can be inscribed into a sphere of radius 1 foot. Okay, so your cone is, well, it's a sphere, it's a cone inside of a sphere. It's a cone inside of a sphere. So find the dimensions of the cone with the maximum volume that can be inscribed into a sphere of radius 1. So here's a sphere, right? 3-dimensional sphere. Ooh, that's a pretty good sphere. And I want to put a cone inside of it, and it needs to be inscribed. Now, what we mean by inscribed is that it's going to touch the edges of the sphere. So imagine a cone whose base, the tip touches, let's say, the North Pole, and the base touches somewhere on the cone. The base of the cone touches somewhere on the sphere. Like I could do this instead, right? I could make a cone that goes to the equator of the sphere. Do y'all see that cone? That would include around here. Is that going to give me the most area? I mean, not area, volume, sorry. Maybe. Maybe that's the most. See, what do I gain? By doing the equator, I'm the widest I'll ever be, right? But I'm also the shortest I'm ever going to be. If I come down on that from the equator, if I come down a little bit, I'll touch around here, and then I'll be something like that. So now I've given up width, but I've gained height, haven't I? So what are the dimensions of the cone that would give me the greatest volume? Does everyone understand the concept of the problem? These are classic problems. Another one is a right cylinder inside of a sphere. So a beer can inside of a sphere. That sort of thing. Or a beer can inside of a cone. So there's all these different variations of this type of problem. And I can remember as a Cal 1 student, the first time I saw it, I was like, what the? I was just like, what the heck, man? The algebra in it, or the geometry in it's just all weird. Yes? Yeah. But the sphere is fixed, right? It's just sitting there. And there's an infinite number of cones you can put inside that sphere that would touch the North Pole and touch along the edge of the sphere. You imagine moving down, it would get wider, and then it would get more narrow, right, but taller. So each one of those cones has a different volume. Which cone has the greatest volume? Maybe. That's a good conjecture, but there's only one way to show it, and that's by finding an objective function, finding your constraint, and then optimizing it. So let's go through this process. What do we want to optimize? Optimize what? Optimize the volume of what? Of cone. Now, if I'm going to optimize the volume of the cone, I may as well start talking about some dimensions here on this cone. I'm going to get rid of the blue cone. You might need to redraw the whole thing. I'm going to work with this red one. Maybe I'm not. Oh, shit. I erased my whole damn cone. Yeah, I'm just going to start my whole damn thing over. Never what? I didn't hear that. What? Never put what? Yeah. That's all crooked, too. Oh, well. Who cares? Okay, we've got a cone inside of an egg. So that cone has a height to it, doesn't it? The cone has a height. I'll call it H. And that cone has a radius to it, which I'll call R. And do you agree that depending on how I design the cone, the height will be different and the radius will be different, right? None of those are fixed as I change the shape of the cone in there. All right. What is the volume of a cone? Because that's what we're trying to optimize. What is the volume of a cone? Volume of a cone is 1/3 pi r squared h. That's what we want to optimize. Right now, the volume depends on how many variables? 2, r and h. What do I need to get it down to? Just 1. So I need somehow to come in here with a constraint. What is my constraint? I have to live in the sphere, right? And the sphere is fixed. But how is that going to get me the constraint? Yeah, I mean, this is a tough one to see right away. The height could be twice the radius of the sphere, so the biggest the height could be would be 2, right? Because the radius of the sphere is 1? Yeah, I agree with that. Anything else? So the radius could be as big as 1. Agree.